Hello! In this unit we're going to learn about a new derivation technique called subderivations, and we're also going to learn about a new logical symbol called the biconditional. In this video I'll introduce the idea of a subderivation, and then in subsequent videos I'll explain in more detail how subderivations work, and then turn to the biconditional. So here's an argument. Therefore, it's a theorem. And the conclusion is the sentence, if P then Q, then if not Q, then not P. And this is kind of saying modus tollens, right? It's saying, well, suppose you have if P then Q. If you also had not Q, then you could apply modus tollens and you would get not P. So if you have if P then Q, then not Q is also enough for not P. And this is valid, no matter what. This sentence is true in any situation whatsoever, and it's derivable. We can do a derivation of it. But it's a little bit tricky how to do that derivation. Let's see why. So we start, as we always do, by saying show if P then Q, by saying show the conclusion, and in this case that will be show if P only if Q, then not Q, only if not P. And our second step is normal. We say assume CD. But now, what should we do for our third step? Well, there's no premise, so we can't this is a logical truth. We're trying to do a derivation of a theorem, and so we don't help ourselves to any premises. So we can't put in premises, so our third step is there's nothing to do. Our next step would be to apply our inference rules like modus ponens or modus tollens, but we're not really in a position to do that. If we were going to apply inference rules, we'd need to apply them to line 2, and for modus ponens we need P, and for modus tollens we need not Q. But we don't have P and we don't have not Q. We don't have either of those, and so we can't immediately apply modus ponens or modus tollens. And not only that, but there's nowhere to get P or not Q from. It's not just that we say have, oh, well, if we had not P, then we could apply double negation and we'd get P. Not only do we lack P and lack not Q, we lack any other lines to get them from. So it's not clear how we can proceed. We don't have any premises, and there's no way we can do modus ponens or modus tollens. Now, what do we want? Well, we want not Q if not Q, then if not P for a conditional derivation. That would be nice if we could get it. And we would hope that we could get that using modus ponens or modus tollens. But it's not clear that we can do modus ponens or modus tollens, and it's also not clear where that conditional would come from. The normal way we get a conditional is, well, either it's a result of applying modus ponens or modus tollens to a bigger conditional, or we do we have the conditional in the show line, and then we box and cancel the show line with CD. But again, it's not clear how we could do either of those things. It's just not obvious how we could get not Q, if not Q, then not P, even if we had the material for modus ponens or modus tollens. So what should we do? Well, here's what we should do. We should say show if not Q, then not P. We should say show not Q, only if not P. So what we're doing is we're writing a new show line. Always the first line of our derivation is a show line, but if you remember what a show line is, we decided that we could write any show line we wanted on the first line. And why is that? Well, a show line just means I'm trying to show such and such. It doesn't mean I have such and such. And so I don't need any justification for writing a show line. But that means you can write it whenever you want. You can write a show line on the first line, but you can also write a show line anywhere else you want. And you can write any show line you want because it doesn't need any justification, because all you're saying is, I'm trying to show this, and that needs no justification. So you can have in your derivation as many show lines as you like, as it turns out. The first line has to be a show line, always, but then you always have the option of adding more show lines. So we're going to need to understand a little bit more how this works, and we're also going to want to pay attention to these strategy questions. When should you try to write a new show line, and when you decide that you should write a new show line, what one should you write? Well, in this case, we decided to write show if not Q, then if not P, because if we can box and cancel this, if we can cancel this show line, we'll have if not Q, then not P, and that in turn is what we need to box and cancel the main derivation. So we've chosen this show line because once we box and cancel it, it's also going to let us box and cancel the main derivation. So let's see how that might work. So now that we've introduced this new show line, what we want to do is show if not q, then not p. Having shown that, we'll then return to the main derivation, but right now we want to show if not q, then not p. Well, whenever you have a show line, if you can, if it's a conditional, you want to make a conditional assumption. And we are trying to show the conditional if not q, then not p. So the way we want to do that is to reason from not q to not p. And so the way we'll do that is by starting by assuming not q. So let's do that. Because we're right now trying to show if not q, then not p, we can make this assumption. And this assumption is not a good assumption to make if all you're trying to do is show line 1. But right now, we're trying to show line 3 in the context of trying to show line 1. And given that we're trying to show line 3, this is a perfectly reasonable thing to do. If we can get from not q to not p, then we will have shown that this conditional is true, given everything else in the derivation. And well, now it's going to be straightforward, because if we look at line 2, we can still use line 2. No reason why we can't. And line 2 and 4 interact. 4 is the negation of the consequent of 2. And when you have a conditional and the negation of its consequent, you can apply your second favorite rule, modus tollens. And that gets you what? It gets you the negation of the antecedent of the conditional. And the conditional is if p then q. We have not q, we get not p. And hey, look, that's what we want to box and cancel the conditional that we're working on. So we can go ahead and do that. We'll say 5cd, because 5 is the consequent of line 3, and line 3 is the show line we're currently working on. We're not working on the show line at line 1 right now, because we've introduced the second show line. So we go ahead and we say we've got 5cd, because 5 is the consequent of line 3, and that lets us box and cancel line 3. So good. Now, when we box and cancel here, the only line we're able to box and cancel is line 3 at this point. With as of line 6, we have to box and cancel line 3, and there are really two reasons for that. One is just that not p is the consequent of line 3, and so it fits with cd, whereas the consequent of line 1 is a larger conditional, and so 5 isn't the right sentence to box and cancel line 1. But also, our reasoning for they got us to line 5 relies on the assumption that we made on line 4. And that assumption that we made on line 4 is fine to make as long as we're trying to show line 3, but it's not an appropriate assumption to make if all you're trying to do is show line 1. And so our line 5 depends upon our line 4. And so it wouldn't be legitimate, it would be mistaken, we would reason invalidly if we said, oh, I made this assumption appropriate for one show line, and now I'm going to use what I got from that to cancel a different show line. So whenever you introduce a show line, that's the only line you can cancel. You can only cancel the closest show line from whatever line you're on when you write down a box and cancel justification. The only line that can be canceled is the closest show line. No other line can be canceled. And so as of line 6, the closest show line is the line 3, and so that's the line we have to cancel. You can't cancel other lines because we made this assumption on line 4, which is fine for showing line 3, but is not okay for showing other lines. And so you can't as long as you're relying on that assumption, you can't cancel lines besides the closest show line which produced that assumption. Okay, but so we've canceled line 3, good. What that means is that we've established that if not q, then not p is true. Well, so what should we do? We should now box and cancel the whole derivation, because line 3, if not q, then not p, that's the consequent of line 1. So having the consequent of line 1 on line 3, we apply cd, and that lets us box and cancel line 1, and we've completed the derivation. We can use line 3 now that it's canceled. When you cancel a show line, that means you've established that that line is true given the premises. And so when we box and cancel line 3, we establish that if not q, then not p was true if the premises are and any of our assumptions. There are no premises in this case, so what we've really established is that given the assumption on line 2, line 3 is also true. But the point is, again, when you cancel a show line, you've shown that it's true, and so now you can appeal to it. And that's what we do on line 7. We box and cancel at line 6, we box and cancel line 3. At that point, we can then use line 3, and we say, aha, 3 is the consequent of line 1. Remember, that's why we actually wrote line 3 in the first place, and then we box and cancel line 1. We couldn't use line 3 before that, partially because we were inside of this derivation, but also just we hadn't shown that line 3 was true yet. an uncancelled show line you can't appeal to because you don't know that what you're trying to show is true yet. The reason why you can write down any show line is because you're only trying to show it, but for that very reason, you can't appeal to it. You can't use it until you cancel the show line, because it's only at that point that you've shown, aha, the thing I was trying to show really is true. This also explains why we have the boxes. The boxes cancel our reasoning, or they contain our reasoning, but they also show which parts of the derivation depend upon which assumptions. So in particular, if we look at, well, we have lines 4, 5, and 6, and we have a little box around them, and that indicates that they rely on the assumption that we made on line 4. And it's fine to use that stuff as long as we're working on line 3, but then we say once we've shown 3, we don't want to appeal to it anymore because it relies on the that assumption that we're now not using anymore, and so we box it to say, aha, we can't use that material anymore. The material inside of the box on line 4, 5, and 6 depends upon the assumption on line 4, and as of line 7, we're not helping ourselves to that assumption anymore, so we can't help ourselves to anything that follows from that assumption, and so we draw a box around that stuff to say we can't use it anymore. Okay, so this is an example of a derivation including a subderivation. In the next video, I'll spell out a little bit more precisely exactly what the rules for subderivations are, how they work, and then also talk about strategy. When should you do a subderivation, and what subderivation should you do when you decide to do one?